Hi everyone. In today's installment of Programming for Lovers, we're going to count the number of times that a pattern occurs within a longer string. To do so, we will need to get comfortable with how Go handles substrings, or contiguous sequences of characters within a string. If you like what you see, please like, subscribe, and join our course at programmingforlovers.com. Let's code. To get started, you'll notice that I have created a directory called Substrings within our Go src folder, and then I've created a file named main.go within Substrings, and I've started to populate it with a little content. I've got a print statement that says we're going to work with substrings and subslices. I've also, for the sake of convenience, added a couple of algorithms at the level of pseudocode that we're going to implement as part of this code along. One is a function called PatternCount that counts the number of times that a string pattern occurs in a longer text. The other is a function called StartingIndices, and that counts the not just the number of times that the pattern occurs in text, but actually identifies what those starting positions are as well, so it will return those starting positions. You'll notice that the structure of those functions is somewhat similar, and we'll get into that when we discuss more about these functions as part of the code along. I would like to begin, though, with a little bit of a statement about substring and accordingly Subslice indexing in Go. So the first thing I would like to do is declare some string. I'm going to call it S, and I'm going to have that string have the value hi lovers ! And if you notice in the pseudocode, the notation that I have here is going to use the notation text of I to I plus k with a comma in between them to indicate a substring of text starting at position I of length k. So we add k to that starting position to indicate the length. That also means that we will go up to but not including position I plus k. So we'll start at position I, we'll go up to position I plus k minus 1, but we won't include that next position I plus k. I'll show you this in practice. In Go, we're not going to use a comma. We're going to use a colon. And so, say for example, I wanted to print the substring of S starting at position 1, having length 5. So the symbol at position 1 is this I, and if we're going to have a substring of length 4, 5 minus 1 is 4, we're going to go I space L and then O. And you'll notice that O is at position 4 of this string, H is at position 0, I at 1, space at 2, L at 3, O at 4, and so we're not going to include the V at position 5. So we go up to but not including 5. And so I'm going to save our code. I'm going to open up the terminal here at the bottom, and I'm going to cd into src and then substrings, and I'm going to compile with go build. And then I'm going to run with /substrings or just substrings.exe if you're on a Windows machine. You're going to see that what gets printed here is I space LO, which is what we expected. The second thing I want to point out is, well, what if we have a substring that's at the beginning of the string or it's at the end of the string? And those are called respectively a prefix or a suffix of the string. So if we wanted to print out, for example, let's say the prefix of length 7 of our string hi lovers. Well, let's print that out. We know it's a prefix, so we would start it at position 0, and it needs to have length 7. So the difference between the second index and the first index is 7. And let's say also that we wanted to print a suffix, say starting at position 4, going up to the end of the string. Now then the question becomes, what is it that final element should be? And I want you to recall that with strings or with arrays, the indices of the string are going to range between 0 and the length of the string minus 1. So it'd be very tempting to type in length of S minus 1 here. After all, we're going up to the final symbol. But remember that we do not include that final symbol indicated by the final index of that substring. So instead, we need to give it length of S. So I'm going to save this, and we're going to compile and run again. I'll go build and run again. And we'll see the first string that gets printed is high space love. That has length 7, and that's a prefix. It's at the start of high lovers. And then we also see overs, exclamation mark, get printed because that's the suffix starting at position 4. I'll point out what I meant again, which is if I made that -1, we're going to lose the exclamation mark when I compile, and when I run, we lose that exclamation mark. So I want that length of s to be there. However, when I save this, that length of s gets grayed out. You might wonder, why is that? The reason why is because Go also has a shorthand here where if I'm referring to a prefix of the string, I don't need the initial 0. If I don't put that 0 there, Go is going to automatically infer it. And likewise, if I don't put the length of s at the end of a substring index, then Go is going to automatically infer that that's what I mean. So that's what we would use in practice. And if I save that, compile, and run, you'll see the same 2 strings get printed because everything is going to be okay. Subslice indexing works in the same way. So say that I wanted to declare a slice, and let's have it be length 6, and it's going to contain integers. And then let's give it some values too. So what I'm going to do is I'm just going to range over this slice, give it some values, and I'm going to set them to the first 6 odd integers. So I'm going to set a of I is equal to 2 times I plus 1. So those values are going to be 1, 3, 5, 7, 9, and 11. And I can see that if I print our slice A. So if I go into the terminal and I compile and then run, I'll see 1, 3, 5, 7, 9, and 11 get printed. Let me show you some subslices. So say, for example, we're going to print A of 3 to 5. That's going to be the subslice starting at position 3, having length 2. 5 minus 3 is equal to 2. So position 3 of that slice has the value 7. So I should see the 7 and the 9 get printed. When I save, compile, and run, that's what I see. I can use the same type of shorthand notation for prefix subslices and suffix subslices too. So in particular, if I wanted to print out the prefix subslice of length 3 or the suffix subslice starting at position 4, then I would use that notation that you might think. I'll save, compile, and run, and we see that 135 gets printed, which is the prefix of our slice of length 3, and 911 gets printed, which is the suffix of our slice starting at position 4. That's my quick overview of substring and subslice indexing. And what I would point out is that if you want to take a look at the pseudocode for these 2 functions, you actually know enough as of this moment in time to go ahead and implement these functions if you would like in Go. I'll leave that to you as an exercise if you would like. Otherwise, I'm going to continue on. So feel free to pause the video. But in the meantime, I'm going to write our PatternCount function. And the first thing I'm going to do is have a function comment and say what it does. So PatternCount takes as input 2 strings, pattern and text. What is it going to return? Well, it returns the number of times that pattern occurs as a substring of text, including overlaps. And what that means is I truly want to count every single time that pattern occurs as a substring of text, even if 2 of those occurrences overlap. And when I check this function, I'm going to show you an example showing you what I mean. For now, I want to write the function. So I have my PatternCount function. It's going to take a pattern and a text as strings, and then it's going to return an integer. How this function is going to work is we need to declare some variable count. It's going to start off as equal to 0. Who knows how many times we're going to find a match. At the end, we're going to return count. And then we're going to range over the text. And we're going to increment our count variable every time we find a pattern match. Okay. So I might say, well, I need to range over the text for I colon equal to range over to the text. And then I say, well, is it the case that the current substring matches my pattern? And so I need to know how long I want to look in the text. I need to know where I'm going to end my substring. So it will be helpful if I declare k to be the length of pattern. And now when I'm ranging through the text, I can check, is it the case that pattern is equal to the current substring of text. So if I'm ranging over all the possible starting positions, I'm going to be checking in text at starting position I, I'm checking against the substring here of length k. So I need to have I plus k as my final index there. If that's the case, then I want to increase count by 1. So I'll have count plus plus. And now we're ready to check this function. So I will give you a hint. There's a bug in this function. You might like to pause for a moment and see if you can figure out what it is. In the meantime, I'm going to save this. I'm going to compile it. And the bug is not a compiler error. So when I save this and compile, everything is fine. Let me go in and set pattern is equal to ATA and text is equal to ATA. So that's an example where I'm actually going to have two occurrences of ATA that overlap by one symbol. Let's print out what we have when I call PatternCount of pattern text. I've saved that. Let's compile it and let's run. And you'll see that we get a runtime error. And the runtime error says slice bounds out of range up to 6 with length 5. The runtime error occurs at line 39, which is here, line 39. And that came from line 28 of main. So it's when pattern count got called, we have this line of the code here. Getting that a slice or an array is out of bounds is one of the most common runtime errors you'll ever encounter, not just in Go, but I guess really in all of programming. And even though it's a frustrating bug that we all get, myself included, ultimately it boils down to one of only two things happening. One, you tried to access a value that was negative. So you had a negative index, and you tried to plug that into a slice or a string as an index somehow. Or you tried to access an index in some way that was beyond the length of the string or beyond the length of the slice or array. So it could really only be one of those two things. And the question is, well, there's something wrong with us calling text of I to I plus k. How could we figure out what that is? And a natural thing to do here would just be to print the value of I right before this line, because it'll at least tell us which of these things it is. There's information lurking in this error message that it's actually that we've accessed something beyond the length of the string, but I can also just get that with printing the value of I. So if I save that and compile and run once again, here is my panic where I get the runtime error, and now I see that the last thing that gets printed is 3. I could do a little better with saying I is, comma, and then I, because we're printing a lot of things, so I'll show you that again. I starts out at 0, then it's 1, then it's 2, then it's 3, and that's the point at which there's an issue. So we could go look at our example, and we could say, all right, well, in this particular example, text is ATA, it has length 5. Pattern is ATA, it has length 3. So k is equal to 3. And the problem happens when I is equal to 3 as well. So this means that we're ranging a window of length 3 along the text. We start with I is 0, then we have I equal to 1, then we have I equal to 2. And when we get to I equal to 3, we're going to be accessing the substring starting with that T of length 3, but there's no such thing. We have TA and then we hit the end of the string. And this should elucidate to us what the problem actually is. In this particular case, what's happened is I equal 0 was a substring, I equal 1 was a substring, 2 is a substring, but I equal 3 we should not be accessing because there is no such substring of length 3. And that bug was resolved. Actually, it was already resolved in our pseudocode. So in our pseudocode, I had for every integer between 0 and n minus k. But I wanted to point out how easy this type of ranging issue is to make. I also wanted to iterate that the underlying idea here is that if you have a string of length n, here n is the length of the text. If you have a string of length n and you have you're looking for substrings of length k, there are always n minus k plus 1 substrings of length k in that string of length n. This is something that computational biologists will have imprinted in their memory forever because it's something that we use a lot because we're always working with substrings of strings. In particular, what this means is the starting positions of all those n minus k plus 1 substrings are going to range between 0 and n minus k inclusively, which means that I need to not range over all of the text, but instead start I at 0, range I up to and including n minus k, increasing at each time. So that way we're not quite going up to the length of the string, but we're going to stop it at the last substring of length k. This also assumes that I defined n to be equal to the length of the text, so I should do that too. One minor note is that I actually prefer indexing over the for loop in the same way that we think about indexing a substring. So with a substring, we have the substring starting at position I, going up to, but not including I plus k. So I tend to have for loops that have the same type of structure. I will have I starting at 0, I going up to, but not including n minus k plus 1. And hey, that's the number of k-mers that we're interested in, i.e. the substring number of substrings of length k. And so I just kind of prefer this way of writing these inequalities. Let's save that, and let's run our code again. I'm not going to need to print out I don't think this time, because I think our code is going to run without error. So when I compile and then I run, the last thing I see printed here is 2, and that was what I wanted to see printed as the number of times a pattern occurs in text. And all is right with the world. We were able to pick up the first occurrence of ATA and the last occurrence of ATA, which are actually at prefixes and suffixes. One more thing I would point out here before we implement starting indices is that technically there is a built-in function for counting the number of times that a pattern occurs in a text. And if we import the strings package, I'll just add that to our imports. So if we import the strings package, I'm also going to print out strings.count, and this function technically takes the text first and then the pattern. As long as you're consistent, it doesn't matter which order you use, but this built-in function from the strings package wants to see the text first. And I want to save this, compile, and run to show you that actually our function, which included overlaps, counts the number of pattern occurrences here as 2, whereas this built-in function only counts them as 1. So it will ignore overlapping occurrences of the pattern. As soon as it finds this pattern match of ATA, it then jumps ahead to the remainder of the string. And that may not be the type of behavior that we want. In particular, for this problem that we wanted to solve, we wanted to include the overlaps. I think there's a completely valid reason for doing so. And the greater idea is that just because you have code that's built in from some package, it doesn't mean it actually completely solves the problem that you're interested in at that moment. So you always might need to write a little bit of code on your own, even for something that might seem as simple as counting the number of times that a pattern occurs in a longer text. Let's move on to looking at starting indices. And the thing that I would point out is just how similar these two functions are. Remember, starting indices is also going to take a pattern and a text, but instead of counting the number of times the pattern occurs, it's going to identify the starting positions that the pattern appears at within that longer text. So it's going to return an array or slice of integers corresponding to those starting positions. But everything else here is pretty much the same. I'm going to set n and k as the length of text and pattern respectively. I'm going to range over all the possible k-mers or substrings of length k of text, and then I'm going to check, is the current substring of length k equal to pattern? And if so, rather than incrementing count, I'm going to append the current position I to my positions, and that's what I'm going to eventually return. So everything there is very, very similar, and I'm going to write this function essentially following that same structure. So I will have starting indices, takes as input, two strings, pattern and text. What is it going to return? The collection of all starting positions of pattern as a substring of text. I mean, technically including overlaps. So we're going to have a function called starting indices that takes pattern and text as strings, and it's going to return an integer. And we can look at our code for help here. I don't want to copy the code over, but I will, because I want to go through it line by line and make sure that I'm not copying code over that I need to truly edit. But rather than declaring a count variable, I'm going to have a positions slice that I'm going to start off as having length 0, because just in the same sense that I don't know in advance how many times this pattern is going to occur as a count, they may occur not at all. And so I don't know how long to set that slice in advance. At the end, that's what I'm going to return. And I'm going to have the same general type of structure. I'm going to set n equal to the length of text, k equal to the length of pattern, and I'm going to range over the text. And every time I find a match, I'm going to append the current position. So if we find a pattern match. So I'll say for I colon equal to 0, I'm going to use my less than notation, n minus k plus 1, I plus plus. And then if it's the case that pattern is equal to the current substring of length k, i.e. text brackets I colon I plus k, then we are going to append the current position to our growing collection of positions. Just need to make sure I have double equality there and we're good to go. And so I'll save that. That felt very similar. There is a maxim in programming, which is anytime you find yourself copying code or writing code that's very similar to what you've already done, you probably can be doing something a bit more efficiently. You can either use a subroutine or notice that these problems are similar. And in this case, noticing that these problems are similar helps us use one problem as the solution for the other. In other words, if I'm able to solve this pattern count problem and know the number of occurrences of a pattern in a string, it doesn't actually help me know where they are. But if I know where they are, if I'm able to identify the starting positions, and I'm really doing the same task, ranging over and looking for pattern matches, if I'm able to know where those positions are, then I immediately solve the pattern count problem, because I can just figure out, well, I just know what the length of this position slice is, and that will tell me the number of pattern matches that I have found. So solving this problem solves the pattern count problem for free. And that means that technically, we don't need all of this code. I'm going to comment it out because I think it was instructive. But the only thing that I need to do is call starting indices on pattern and text, and that gives me that slice of starting positions. And what I'm interested in is how many positions were there? In other words, how long was that slice? So I really care about the length of that slice, and that's all I need to return. So in practice, I'm just going to return the length of the collection of starting indices of pattern within text. And I don't need that other code. So I will save that. And then the idea is, let's make sure that our function is actually working. So let's run pattern count again. And I want to also call this on starting indices. So we should see the pattern count tells us that this occurs twice, and the starting indices that we should find are at position 0 and at position 2. So I've saved that. I'm going to compile. And of course I get a compiler error. Starting indices, pattern of type, value of type int for length. Well, that's not good. I know what happened. Line 69, let's see. Position is a slice events of length 0. It says you cannot use positions variable of type slice int as int value when you return. Why did you try to return something that's a slice? I wanted an int. So we just need to change that. Okay. Some real-time compiler debugging. All right. Now we're going to save and run. And as we had hoped, we print the number of times the pattern occurs in text, followed by the collection of starting indices that we find. So we print 2, followed by 0 and 2, and that's what we'd hope to get. Keep in mind that general principle. A lot of times when you're solving a problem, it's not actually any more complicated to solve a more general problem, and then you can use that solution of that more general problem to help you, which is what we did here. We basically solved 2 problems for the price of 1. That's it for this video. I hope you'll join me for the next video. Please like, subscribe, or stick around for the next code along. Regardless of what you do, I'll see you next time. Happy coding.